All right. Welcome, everyone, and thank you for coming. This is the defense for our project, which is called Car Racing with Reinforcement Learning. We are the team under the supervision of Juan, Nieto, and our team is composed of Xavier, Canal, Rubén Martínez, Jaime, Pedret, and Alvaro, Navas. We'll talk briefly about what we already talked about in our defense on our project review presentation, and we'll explain our final results, what we learned in this project, and that's pretty much it, essentially. So just as a recap from a few weeks ago, the main goal of this project is to learn about reinforcement learning and to apply it in a real-world environment. One of our members has a robot, and we thought it would be a cool idea to teach it to go around. But because we didn't have access to the tools to teach that to work with that robot for the rest of us, so we decided to use an environment called OpenAI Gym, which is a framework that allows us to work with these environments. However, our project was too ambitious, so it ended up split in two parts, which is the environment part, which is what we'll talk about, and at the end we'll talk about the robot part. So I will now explain what our environment was about, the car racing environment. Well, these are the goals that we talked about in the presentation in the project review, which is learn about reinforcement learning and how to train a neural network, and how to train and improve our results, interpret the results, and develop team skills that would be useful in a professional setting. So this is OpenAI Gym, which is a framework for reinforcement learning. It allows us, well, not only us, but both students and researchers to test and develop reinforcement learning algorithms, which, if you may recall, are we don't work with data sets, but we work with agents that develop they make their own data sets by exploring an environment, and then we train a neural network in order to decide what to do on that environment. This is car racing, which is sort of like an old-style video game, Atari-style video game. There's this car which goes through a track, and what we call the state is each frame of the game. So we receive the state, we decide what to do, as in go forward, turn left or right, or brake. And when we use that action on the environment returns a new frame or a new state. And also it gives us a reward, which is a value that we use to evaluate what we're doing on the environment. So these are the resources we used. As you can see, we have a few local PCs which had graphic cards. And after experimenting a little bit with Google Cloud, we found out that we could do faster training most of the time on local environments. So we only used Google Cloud instances at the end of the project. So I will now let my colleague Jaime speak.
Yeah, so now we will present the final results with the test we've done so far in this project. First of all, we will see the results using the reinforced basic algorithm with vanilla policy gradients. Here we are seeing an image of our final neural network architecture. So the input to our neural network is a stack of 4 frames, which are the states Alvaro already commented. They go through some layers of convolutional, some convolutional layers, ending up with some linear layers. And the output for our networks are the actions we allow the agent to do. Finally, we have the softmax activation functions as we want probabilities on our output. Here on the graph, we are seeing the average reward we get on each episode. We run up for this testing, we run up to 20,000 episodes. Our target was 900 as reward, but with this algorithm, we only got average of 400. And here we can see a video of what the agent was actually doing. So it seems it's turning left quite good, but at the end, it loses track. It seems it doesn't capture quite good the right turns. Now I will explain an update of this reinforced basic algorithm.
Yeah, our second implementation that for our reinforcement learning method was reinforced with baseline, which is essentially taking the value state function and applying it to our objective function in order to reduce the high variance that we found with the original reinforce. What that means is that our explorations are better in a way because they're more focused, and we have much better results and with in a much quicker fashion. The only difference in the network is that, as you can see in the end, there are 2 heads rather than 1. One head is the same as always. It only calculates the action, which is called the actor head. And then there's a critic head, which calculates that value state function, which is necessary for updating the network parameters. So as you can see in the video below, well, maybe this track is not as complicated as the other one because tracks are randomly generated, but it drives pretty well and it consistently stays on the track. And we were pretty happy with these results. And we are confident that with perhaps a little more fine tuning, this particular algorithm would be able to solve this environment.
Yeah, and the next step in the evolution of the algorithms of reinforcement learning, we went to implement the proximal policy optimization algorithm, which essentially has the basic structure in terms of neural network, observation space, and outputs. But the huge advantage of PPO was that on every episode, the network would see multiple times the same episode. So in this PPO, the basic change is that there's a more complicated way to compute the loss and a more complicated way to structure the algorithm, how to train the network. We have usage of memory. You have usage of different transactions to train that. So with that, our current status is that we could not obtain good results with this algorithm, and because what we've seen is that with 1.5 episodes, episodes, we didn't see any positive rewards. So we expected to have positive rewards in fewer steps episodes than baseline and reinforce, and we couldn't see that. So we have the two hypotheses right now in that moment, which is one, we should do better hyperparameter tuning exploration, and two, check if our algorithm has a conceptual bug or something in there. Next slide.
So now I will explain the learning process we went through just to obtain these results we already presented. First of all, we needed to learn GitHub. Some of our members, like me, didn't know how to use GitHub, so I learned on this project. We also created this deep learning virtual machine on Google Cloud. We also needed to figure out how we were gonna measure the metrics on our model. So we decided to use TensorBoard, and we also used Seaborn just to know what action was actually the agent applying. So for example, here's action number 6 is turn left. So here we see a big spot on left. So actions, we could track this way the actions. We also faced a huge problem at the beginning. We were getting out of memory issues. And finally, one of our team members, Xavier, discovered that there was a memory leak issue on the environment itself, and it was already solved and on the master branch for the environment. So we could go on, but we lost quite a lot of time on this point. The checkpoint, we were tracking saving checkpoints on our model, so saving parameters, it's every 10 episodes. And we also used some wrappers like converting RGB images to grayscale, stack the frames, frame skipper, which applies same actions to consecutive states. So some other wrappers to make videos, and an early stopper wrapper, which allows us to produce the done state at certain, for example, where they are on the grass too much time. Finally, on the reinforced implementation, we were stuck at the end of the first milestone because our agent was always applying the same action and the entropy was collapsing. So at this point, we decided to go directly to the reinforce with baseline and check if we were getting better results. So conclusions for the middle milestone, we did all what we wanted to do, but we didn't have a good implementation, or we had not as good as expected results with the reinforce. So Alvaro will explain now the second milestone.
So for the second milestone, we decided it was to achieve an implementation with reinforce with baseline algorithm, and it turned out to be one of the most productive things that we did, because it forced us to reevaluate what we were doing, and in the process, we found lots of things that we could fix. Please excuse me, my phone is ringing for some reason. Okay, so the first thing we found out was that learning rate had a huge impact. What we did, we found out by studying the code that we had chosen, for some reason, a learning rate of 1e minus 2, which turned out to be a very bad decision. And when we changed it to 1e minus 3, we suddenly jumped, we had a huge jump in quality. So in the graph on the left, you can see that's the running reward, which is our metric to evaluate how well we're doing in our environment. And the task is, the environment is considered solved when you get a consistent reward of over 900 in value. So in the graph in the left, you can see that we have values that barely exceed 30. And in the right, only by changing the learning rate without doing any other changes, we suddenly have values nearing 700 in value, which is what it was super impressive for us. Other things that we learned, well, by finding this, we went back to reinforce, and we decided to do learning rate experiments with different values. And we found out that specifically for reinforce, we found the best results by lowering actually the learning rate, and a value of 1e minus 5 was ideal. And we found the best results, as you can see in the graph below, in the green line. We did also, well, as explained before, we had to change the heads of the network because we had to calculate an extra value, and we had to reevaluate what we were doing. And we found out that for some reason, we had chosen the log softmax activation function at the end, which was a mistake because conceptually we should be using a softmax. But we were confused because there's lots of logarithms we had to use due to reinforcement learning and, you know, like derivatives, etc. But for some reason, it was working with log softmax. But we changed that, and we still don't know why it worked with log softmax, but we did change it, and we believe that it was a very positive impact. We also added a new convolutional block to the network. Also, the other important bit is the action set. Yeah, go back to action. Thank you. We were using, we are using discrete actions, which is we have discrete values to input the actions. So we have ones, well, like here in the left, you can see we have 1 throttle, 2 throttle, 3 throttles. So 3 different values of throttling to go either faster or slower. But we started experimenting with that, and because we had an issue, we found out that the network was never learning how to brake. And what we did is by limiting the top speed, or the top acceleration rather, and by forcibly applying brake when turning, we could manage to control the top speed, and we found much better results, even if it's not ideal in the sense that it's not braking in before at curve, but it's much better result than what we were getting. And so as a conclusion for the second milestone, we updated our implementation because we polished our code and we found my bugs. We updated the metrics in the sense that we finally got the hang of TensorBoard, and we managed to output much better logs. And it helped us to understand both the model, what we were doing wrong at that moment and before, and we had better results in both algorithms that we had implemented so far. So now Xavier will explain PPO.
Okay, so the third milestone was mainly based on how to implement or evolve the previous algorithm to the PPO one, right? Right at the beginning, what we did is like follow the PPO paper from OpenAI company, and we started the implementation. It wasn't an easy step to approach, to introduce these huge changes in there and understand the whole loss based in 3 different components: the entropy, the value function, and then the ratio one, the clipped one. So right after we tried the hyperparameters that the paper suggested for their environment, and our surprise was that there were really poor results in terms of it, with a bunch of episodes visiting the network. Our running reward was still really low, under 0, when in the baselines it was like with 1,000 episodes, it was positive values, right? We expected, actually, since we were visiting for 1 episode, we were visiting different times the same episode, we expected to have like positive values in fewer episodes, right? So next step, please. So after that, we've decided, okay, let's change, for example, the rewarding system, and let's change also the observation space. So what we did is we introduced it in our environment, a couple of wrappers, the early stopper, saying that, okay, if the last 50 steps, you have an average reward of negative reward, then you should stop, because you're not supposed to go to the grass. And also the green penalty, changing the reward and saying, okay, you have a higher penalty when you are in the grass, trying to guide the algorithm to be in the track, right? So after that, what we see here, for example, is with this change, we got positive results. For example, with only 200 epochs, you see that the algorithm was throwing rewards around 60. But at the same time, the entropy collapsed to 0, meaning that the network was really, really sure about what it was doing, and also not preventing to explore other scenarios. So our hypothesis said, okay, it is going ahead. It has learned to go like a straight, but when it finds a curve, it's not able to manage to turn right or left. Next slide. So based on that scenario, we said, okay, it's something, it's learning, because it learns how to go straight. So okay, we should do some hyperparameter tuning. So we started with the Raytheon, and we started some experiments. We experimented in various things. For example, in the loss coefficient ratio for the value function and the entropy, and also changing the PPO epochs, the epochs you're visiting the memory, the experiments, in order to try to prevent overfitting on the action of going straight. But the results were not better. As you see here, our running results are around minus 70. However, it's only with 1,000 episodes, 2,000 episodes, 1,000 epochs, which it should be enough. So we are at that point that our hypothesis, or we have a bug in our algorithm, or we should expand working on the hyperparameter tuning. Next step. Okay, and for presenting and checking how reliable are our algorithm, what we've considered to do is we check 3 different sets and we run experiments on them. We put a name, we pet them, and we set the Jan LeCun's 1 because it's his birthday, a 1 boring 1,000, and a seed 1, which is today. And what we've seen is that the rainforest, the basic vanilla policy gradient, is not that robust. As you can see on the graph on the top, there's only 1 seed with actually evolving and showing some progress, whilst the other 2 ones are really like on the 0, near the 0. Instead, in the rainforest with baseline, we can see a little bit of more stability and robustness, because it shows more or less the same tendency with the 3 seeds, and exceptions of the blue one, that there's like a huge collapse at what point. But we can see that the progression and the evolution with different seeds are quite stable and quite the same. So we can definitely say that it's a little bit more stable and robust, this one. So as a result, in this third milestone, we can say that, okay, we didn't achieve the solving the car racing environment with PPO. However, we did a nice implementation of it, understood all the loss and the different components of that loss. We update the metrics, We prepared everything to run our code base in the most smooth way and ready for throwing trials and experiments for the hyperparameter tuning, and ready for validate or invalidate our current hypothesis. And now time for Rubén.
Yeah, in this case, we have work with a gym environment that is a maze, as you can see in the picture, and it uses a simulated version of a real world robot called Turtlebot. And we have chosen this environment because we have a physical unit of this kind of robot. And the idea was to train a reinforcement learning model in this environment. So after that, we could deploy the trained model in our physical robot, as we could see at the end of this talk. Well, about the states, the sensor of the robot that we have used to capture each state is a LiDAR. You can see our physical LiDAR, I think. Yeah, and this LiDAR emits 360 laser beams around itself with an angle of 1 degree between two contiguous laser beams. So with each laser, we can know what is the distance with any possible obstacle in that direction. And to learn how the LiDAR works and how the data is stored and its order, we developed a ROS program, and this program is included in the GitHub repository of this environment. And using this program, we saw that the data is stored in a Python list. So the element of the 0 position of the list corresponds to the backside of the robot, or 0 degrees, and it moves in a counterclockwise fashion. Okay. And we decide, could you go to the previous slide? Okay, thank you. And we decide to discretize this amount of laser readings to 5 laser beams corresponding to the right side of the robot, or 89 degrees, the right front angle of the robot, or 155 degrees, the front of the turtlebot, or 179 degrees, and the left front angle of the, or 224 degrees, and the left side of the robot. Okay. About the actions, we have also discretized the action space to 3 possible actions that are move forward, turn right, or turn left, which are translated to a combination of a linear velocity and angular velocity. And finally, about the rewards, the configuration of the rewards by default, that we are going to receive 5 points if the last action was to move forward, and 1 point if it was to turn left or turn right. And if the episode ends, we will get minus 200 points. And when does this happen? Well, the goal of this environment is to learn a policy to avoid the robot is closer than 0.2 meters from any possible obstacle in the direction of the 5 laser beams. Okay. Yep. Could you pass the next slide? Okay. Thank you. Well, we have used ROS, which stands for Robot Operating System. And as a summary, it's a framework which allows us to access data collected by different robotic sensors in a remote way from different devices of the ROS network. And we will have several main concepts inside ROS. And the main important one will be the concept of node, ROS node, which is only an executable which implements a task. And one kind of a special kind of ROS node will be the ROS master node, which allows all the nodes to register and communicate with each other. And another important concept is the concept of topic, which is only a data structure used to share data between nodes. I mean, one node could write data into a node, could publish data into that topic, and a different node could read or subscribe to that topic and access to that data in a remote way. Okay, could you pass the next slide? Okay. About the learning algorithm that we have used with this environment, as we tried policy gradient methods with the car racing environment, we decided to try a different kind of reinforcement learning algorithm, in particular a deep learning algorithm. And this algorithm uses two neural networks with the same topology: the policy network and the target network. That's in our case, they are going to be two multi-layer perceptrons, as our inputs are 5 readings from the LiDAR, and they will have 3 outputs corresponding to the 3 possible movements. Okay, the policy network is going to be updated after each step, and the target network is updated, copying the parameters of the policy network periodically, and especially in our case after 1,000 steps. And the reason why we use this delayed network is to make training more stable. It's like saying, well, I have an idea of how to play this game, and I'm going to use this knowledge as a target during some steps. Well, I try several policy network updates until I think something better.
You have like just 1 or 2 more minutes, maybe you want to move forward, okay? Just before reaching 25, okay, minutes, please, go ahead.
Okay, summarizing, you can see in the picture the formula used to update our policy, and how the Q values are updated. Okay, could you? Okay, thank you. Well, what was our first milestone? Well, our first milestone was to achieve the environment working properly, because each version of ROS is very dependent on a specific Ubuntu distribution, and it needs to work with Python 2.7. And to solve that, we have to compile ROS using this flag that you can see in the slide, pointing what Python we are going to use. And another thing that we had to solve was to adapt the LiDAR offered by the simulator, called by the gazebo environment. And we have to discover what were the configuration details of our physical LiDAR, and write those configuration in the gazebo specifications. Okay, and finally we decided to create a Docker file to facilitate the installment process. Okay, and we have also detailed all the instructions if you want to perform the manual installation in your operating system. But you'll need an Ubuntu 16.04 if you want to install in your operating system manually. Okay, well, our second milestone was to get a deep learning model working with the parameters by default, as you can see in this picture. And after a configurable number of steps, we execute periodically a test phase using the policy network in eval mode to choose the next action. We track the cumulative rewards during each test episode, as you can see in this terminal picture. Okay. And how does it translate in the circuit? Well, the agent was able to reach until this point, more or less. And we should play with the learning rate and the epsilon greedy trade-off to increment the change of exploration. Because with this first call, our policy network doesn't take good decisions. Okay.
Next. Let's start finishing with Alvaro.
Yep. Okay.
You want me to play the videos, Rubén?
Okay.
So they can see it.
Okay, play. Go on.
The physical video, or the.
You could play the physical video at the end. Okay. Well, finally, we achieved to deploy the model the training model in our bicycle robot. But as a disclaimer, I have to say that I have lost the screws needed to fix the LiDAR to the top of the robot. And because of that, we'll see that the LiDAR dances while the robot moves. And besides that, there is a problem with the wheel axle of the robot, and it can explain some jerky movements. Okay, but the behavior of the robot is as we could expect with the training model achieved in the simulator. And finally, my partner Xavier is going to talk about the conclusion.
Then I'm going to be 30 seconds long. So conclusion is like we find crucial to spend time of hyperparameter tuning, and also that choosing the actions for discrete environments is a crucial one, and it needs a really close look into the experiments. The reward system also, it's something really important in order to guide the algorithm. And what we realize is that in reinforcement learning, neural network architecture is not that hard to find compared with the algorithm and the ways and strategies to learn to update the policy. Thanks.